All right, let's take a look at the proof of Euclid's proposition number 37. Now, basically what this one says is that if we have two triangles that happen to share a common base and the opposite vertex from that base happens to lie along the same parallel line for both triangles, then those two triangles are going to have the same area. So what we want to show is that the area for the blue triangle is equal to the area for the red triangle. So let's see if we can prove that. Okay, so the first thing that we want to do is construct the line that's parallel to AC, so parallel to this side. So let me turn this triangle off. So that's parallel to side AC that's passing through B. Okay, so if we draw that line, oops, not that one, there, so we draw that line, and we say that that intersects our line through AD at our point E. Okay, then we do the same thing, and if we look at the other triangle, then we want to draw the line that's parallel through BD that's actually passing through C. So if we draw that line, then we say that that's going to intersect our line AD at point F. Okay, now what that does for us is that it actually gives us two parallelograms. So it's going to give us a parallelogram here, AEBC, and it's also going to give us a parallelogram BDFC. Okay. So now what happens with our parallelograms, so notice what we've done in that construction, that those two parallelograms are sharing a common base. So they've got a sharing the common base, and their opposite sides from that base are going to be along the same parallel line. Now, what that means is back from our proposition 36, that the area for those two parallelograms are going to be equal. Okay. Now, kind of recalling our homework problem that we did about our parallelograms and the congruence of sides, which is really Euclid's proposition number 34, what we have there in that case, so let's turn on this triangle, is that this side AE is going to be congruent to side BC. We have side AC congruent to side EB. And then if I put in that extra triangle, then our side AB is going to be congruent to itself. Now, what we've done in that case is to show that these two triangles, so our triangle ABC and our triangle EBA, are going to be congruent by side-side-side congruence postulate. So what that really means is that this triangle ABC actually cuts the parallelogram in half. And so the area for this triangle is going to be equal to half of the area for that parallelogram. Now, there wasn't anything special about that triangle. If we put in the other triangle and we look at the other parallelogram on there, then sure enough, the same thing is true in that case, that opposite sides are going to be congruent, and one side is going to be congruent in itself, so the triangle is going to divide up the parallelogram into half. And so the area of this triangle, so the area of our triangle BCD, is equal to half of the area of our parallelogram BCFD. Okay, so now kind of putting all of that together, so we've got our triangles here. So our triangle ABC is half the area of the parallelogram EBCA, which is equal to the area of parallelogram BCFD, and half of that area is equal to the area of triangle BCD. So each one of those triangles is equal to half the area of the two equal area parallelograms, and so the areas of the triangles have to be equal as well.